Okay, today we're going to talk about how to do some constructions. The first construction we're going to do is the circumcenter. And the circumcenter is basically the point at which, in a triangle, all the perpendicular bisectors intersect. So since a triangle has three sides, it has three perpendicular bisectors of each side, and where those three intersect is called the circumcenter. Now, the special property of a circumcenter is that once you find that point from the perpendicular bisectors, that point happens to be the same distance to each vertex. So the orange is what results from the construction. So the first thing we need to know about is what is a perpendicular bisector and how do we create one. So if we have an acute scalene triangle right here, and I've already pre-measured the sides, if I want a perpendicular bisector, the first part is it has to be perpendicular and it has to bisect. What does bisect mean? It means it has to divide the side into two congruent parts. So in order for you to make a perpendicular angle, you're going to take, you want two 90-degree angles, and so you can take a side and you fold it over up on itself. Now, if you just simply fold a side on top of itself, you can make a perpendicular angle. But if you want it to bisect the side, then that means the endpoint and the endpoints have to match up exactly. So if we match up the two endpoints exactly, I make a 90-degree angle with my fold and with the side, and I make it so that each side is congruent. So we have a perpendicular angle, and we have a bisector of the sides. And we indicate the perpendicular by the little perpendicular symbol. Now, if I were to take my measurement, so let's take a ruler. This whole side is 80 millimeters, and whenever we divided it in half, it's right at the 40 millimeter mark. If you do it again on another side, again, to make it perpendicular, you simply only need to fold the sides on top of each other. But to make it a bisector, you have to fold it end to end. Sort of like if you had a long string and you wanted to find the midpoint of that string without having any kind of ruler or anything, then you would just take the two ends of the string and you would fold it together and you would find the midpoint. So the perpendicular bisector is right here. We usually draw dashed lines on our fold, and we say that this side, the two sides are congruent because it bisected it. So since the whole side is 100 millimeters, the bisector is right at the 50 millimeter mark. So you can see it that way. All right, so that's basically how it works. So let's do one. Let's take an acute scalene triangle, which I happen to have, and we want to make a circumcenter. So the way to make a circumcenter is to draw a perpendicular bisector for each of the three sides. They should, when you fold them, intersect at one point. Now you want to be kind of careful when you're doing your measurements and your folding so that your point actually ends up in the same spot. All three folds end up in the same spot. So again, perpendicular bisector, you fold it on itself. Folding it on itself, overlapping like this, using padded paper is kind of nice because you can see through it. This will give you the perpendicular angle, but having the endpoints touch each other, C and A, make it a perpendicular bisector. All right, so we're going to make this green. And so there's nothing special about the colors. All right, and we know that these two are congruent. And then we're going to make this. Do the same thing for this side. B and C will fold on top of each other. You're only looking at the side that you're folding. And we'll make that red. All right, and interestingly, we're bisecting the sides, but what will end up happening is that the circumcenter, that point in the middle, will end up being the same distance to each vertex or each corner, if you will. It's a vertex when it's a triangle, but it's kind of like a corner if it were any other polygon. So we fold the ends right on top of each other, make a fold all the way. All right, and then this is perpendicular, and we use our tick marks to show that they're congruent. Now they intersect at this point. This point is the circumcenter. So if I did this correctly, it should be the same distance to each vertex. That's what we claimed beforehand. So I like to use the millimeter part of my ruler because it's a little easier to get some accurate measurements. So it looks to me like it is from this line all the way to the circumcenter is 49, maybe 48 millimeters. Let's look at this one. All right, and so again, it looks like about 48 millimeters, and then going from the vertex to the circumcenter, or the circumcenter to the vertex, again, it's about 48 millimeters. So we did okay. Now, why is it called a circumcenter? That's kind of an odd name. Now, circum means around, and center. And so what's the thing you think of when you think around is you think of a round circle. So it means that somehow there's a circle involved here. So a circumcenter is simply the center of a circle, so that if you were to inscribe the triangle inside the circle, this is the same size triangle that we were just using, by the way, and if you were to circumscribe a circle outside of that triangle so that each of the vertices touch the circle, the distance from the center of the circle to any point on the circle is called the radius. And so the distance from the circumcenter to each vertex is actually the distance of the radius. That's why it's equal to each other. So that's kind of cool. So you might ask yourself, what if we had a right triangle or an obtuse triangle? Will the circumcenter always fall inside the triangle? The answer is no. Let's look at a couple of examples. So if we had a right triangle, and a right triangle is inscribed inside of a circle, then we want to use, what do we use again? We use the perpendicular bisectors. So we took each vertex and we folded it onto itself. Okay. And then we took this side and we folded the vertex onto itself, the opposite ends, such that we have a perpendicular line. So this is the perpendicular angle, and we have a bisector. So it's a perpendicular and it's a bisector. And then the last side is this side, so we're going to fold B onto C, and you want to line up the lines just right. And all three of those folds, I don't know if you can tell them on the video, but all three of those folds happen to end up right here. This is the circumcenter. So they were each perpendicular bisectors. They were perpendicular and they bisected each side. All right, these were my three folds, happen to be perpendicular here, okay, and they intersected at this point. So that means that the distance from this point to each vertex should be the same. Let's check it out. So here's the circumcenter and here's the vertex right on the edge. Now when I drew the circle around the triangle with my compass, it was a little bit, it wasn't perfectly accurate. I mean, it was close. And so here I get about a maybe 54, and then going from this vertex, let's look at this one over here, it's about 55, so I was a little bit off, and then from the circumcenter to the edge or to the vertex here is about 55, so that's probably the one that was off. So it's pretty close. So the idea is, again, that the radius, this is the radius of the circle, and then this one happens to be the radius from here to here. And then the last radius going from the center. Again, the radius goes from the center to any point on the circle. So when you use your three perpendicular bisectors, they intersected at the circumcenter. And the result was that the circumcenter to each part of each vertex was the same distance, or the radius. So we've done an acute scalene triangle. We've done a right triangle. What about an obtuse triangle? Obtuse triangles are kind of odd. So if you look at this obtuse triangle, and I went ahead and drew the circle around it so you can sort of see what was going on. Let's look and see what happens. What did we do again? Perpendicular bisectors. So A and B will fold on top of each other so that they line up exactly. We have a perpendicular angle and we bisect. From this point to A and this point to B are the same distance. You can clearly see that. So B and C, we'll fold B to C over. Perpendicular angle. And it's a bisector, so let's go ahead and label that so we don't forget what we're doing here. And then this was a perpendicular angle that we just did, and it's a bisector. And then the last side was my AC side, and so we folded A onto C, and lined up the lines as best as we can. And so that was my third right here. This was my perpendicular bisector. And this is the fold. All right, so the three folds intersect way out here, okay? So if you were to look at the obtuse triangle without the circle around it, so this is the same obtuse triangle, the circumcenter ends up being way out here. And if you look at the circle, it makes sense as to why the circumcenter is out here, because it has to be the same distance to each vertex. So the distance from the circumcenter to the vertex out here should be the same distance as the circumcenter to this vertex, should be the same distance as the circumcenter to this vertex. So let's measure them, kind of get a feel for what happened here. So we have about 44 maybe millimeters, about 44 millimeters here, and look, about 44 millimeters here. So pretty cool. So the circumcenter can actually fall inside the triangle, outside the triangle, or on the side of the triangle. Doesn't really matter. But the goal is that you use 3 perpendicular bisectors of each side, and where they intersected was the center of the circle that would have been circumscribed around the triangle. And then the special property of a circumcenter is that it's actually the same distance to each vertex. So even though we bisected the sides, we got the same distance to each vertex. All right, stay tuned, because I'm going to do a video on angle bisectors and incenters.